Synapses in the nervous system are kind of important because that's how you get information from point A to point B. Very rarely do you have one single neuron traveling the whole length. So what is a synapse? A synapse is going to allow information to travel from one neuron to a second neuron or to an effector cell for that matter. Think the muscle, neuromuscular junction. That's a synapse. So this is how you transfer information from one cell to the next across a fluid-filled gap. Now, if you're wondering, why not just have them touch? Why have the fluid-filled gap? Well, the idea here is if you have them touch, you still have two membranes in the way. So somehow we need to get information from one to the next. And just simply letting a whole lot of sodium ions out into that fluid isn't going to be very efficient. Plus, sodium is just one single messenger. In case we have neurotransmitters, which have a whole wide range we can use instead. So by using those neurotransmitters, it allows us to have a lot of different actions and be more targeted in what we're trying to do. So we'll start with the presynaptic neuron. So pre means before. This is what's before the synapse. We'll get to the postsynaptic in a second. That's the one that comes after. So we're conducting the impulses towards the synapse. We have synaptic bulbs down there. That's, remember, the end. Those synaptic bulbs contain synaptic vesicles. Those synaptic vesicles can contain neurotransmitters. These neurotransmitters can either be excitatory or inhibitory. In the case of excitatory, you're trying to reach depolarization. You're trying to get to threshold. But in the case of inhibitory, we're going in the opposite direction. Usually, it's hyperpolarization. You're trying to prevent a signal from occurring. So we have both excitatory and inhibitory neurotransmitters, and for that matter, there's also excitatory and inhibitory receptors for these neurotransmitters. And then we have the synaptic cleft. That's where the neurotransmitters are going to head into. They'll be released via exocytosis into that synaptic cleft from the synaptic bulb, so the end of the axon terminal. All right, postsynaptic neuron. This is after the synaptic cleft. Postsynaptic neuron is going to transmit away from the synapse. This is what will receive those neurotransmitters and then carry it away. Now, these neurotransmitter receptors, the receptors themselves, are going to be specific to particular neurotransmitters. You can't just have a receptor that says, oh, I'll bind every neurotransmitter out there. Yeah, it doesn't work. There's no universal. They're specific to a particular neurotransmitter or a particular class of neurotransmitters. So what we're seeing here, we have our presynaptic neuron. It's coming down, and let's say the action potential comes down. It's going to then trigger some of these synaptic vesicles, these circles, synaptic vesicles, to go down and release the acetylcholine, or whatever neurotransmitter you pick, into this actual synaptic cleft. Those then diffuse across and bind to these receptors on the postsynaptic neuron. Once bound to the receptors, they then open up the receptors, causing the ions to flow. So once you bind that, the ion channels open, allowing those different chemicals to flow. You're converting a chemical messenger back to an electrical signal. Because what you're trying to do here is by binding that neurotransmitter, sodium and potassium are flowing. You're creating a graded potential. As long as it's strong enough, those graded potentials could trigger a new action potential. So you've gone from this electrical signal, this action potential of the sodium ions moving, triggering the neurotransmitter, chemical, to trigger back to an electrical signal of more sodium ions moving. But again, remember, graded potentials are local events. It's not an action potential. You have to have enough graded potentials to build up to reach threshold, which means the neurotransmitters are binding several different receptors. It's not just going to be one receptor. You might have 3, 4, 5, might have 15, might have 50. All depends on that postsynaptic neuron, how many receptors it has. Now, this might look a little crazy, but here's the point. Threshold is right here, negative 55. That threshold, you can notice this first signal, that gradient potential wasn't strong enough. Didn't get there. The second one was stronger, but it still didn't get there. The third one, it's a little wider, so the stimulus lasted longer. Gradient potentials can be any size and any duration. It's not like an action potential. But still, those first three didn't make it. Finally, this one looks like you might have had 2 or 3 signals all summate or add together. Hit threshold, it would take off. Those are all excitatory. Look at the inhibitory now. Here's different inhibitory ones. They're all hyperpolarizing. They're all dropping lower, further away from threshold, making it even harder to trigger an action potential. So again, these neurotransmitters, and these receptors for that matter, can be excitatory or inhibitory. So let's look at what's called an excitatory postsynaptic potential. In the case of an excitatory postsynaptic potential, you're depolarizing. So we're going towards threshold. You won't necessarily hit it because this is simply a graded potential, but you're going towards it. You're depolarizing. Remember, these channels are allowing both sodium and potassium to flow. More sodium than potassium, but you are having both. With having more sodium, that means you are causing a slow or mild depolarization. Now again, these do not generate action potentials. These are chemically gated channels. You need the voltage regulated channels to trigger an action potential. So this EPSP, excitatory postsynaptic potential, it can trigger an action potential if you're at the axon hillock and if they add together to reach threshold. So there's a big couple ifs there. You gotta kind of add things together. You gotta be where you can generate an action potential also. Flip it around. Inhibitory, or IPSPs, inhibitory postsynaptic potentials. These ones are decreasing your chance of an action potential. They're causing hyperpolarizations. They're trying to move away from that threshold. So you can end up hyperpolarizing because you've more potassium, more chloride. So if you end up having more permeability to these two, it's lowering the actual membrane potential. So it's harder to reach threshold. Basically, the inside of the neuron, or the muscle for that matter, but the inside of the neuron is going to be getting more negative, making it harder to get up towards threshold. So if we're looking at this, you can see the green here is going to be EPSPs, excitatory postsynaptic potentials. You have one here that goes up, and then one here that goes up, and then going up, and going up. But then in between there, you're going to notice that there are some IPSPs. Here's one going down, here's one going down. They're trying to go away from threshold. But one single one by itself doesn't reach threshold. You have to add these together, the summate idea. And if you hit threshold, you trigger an action potential. So I keep mentioning summate or summation. The idea is sub-threshold, nothing happens. Even if you hit negative 56, nothing happens. So a single EPSP, excitatory postsynaptic potential, cannot hit threshold. But they can summate, they can add together. And if they add together, they could potentially reach threshold. If they reach threshold, you then trigger an action potential. So there's 2 ways to summate. First off, we have temporal summation. Temporal, think the base is called time. So temporal is time. What's happening here is the neurons are in rapid fire. So you have basically one single neuron just firing over and over, which means that all of these signals, all of these impulses are hitting the exact same spot on the postsynaptic potential. So it's like one after another, rapid fire. While spatial summation, spatial, think space or distance. In the case of spatial summation, you're going to have a large number of terminals, all firing at the same time. So you have all these different presynaptic terminals coming in to one single postsynaptic neuron. So you have all these signals coming in at the same time. They all add together to pass threshold. So that's spatial summation. So kind of look at it this way. Up here, we have one single signal coming in. Nothing happens. You didn't pass threshold. But then over here, see there's two arrows coming down. That is going to be the idea of temporal summation, one after another, at the same exact point. You can see how the first one comes up and the second one goes further. They add together. They summate. One up, doesn't quite come back to rest, the second goes off. So that's the idea of temporal summation. In the idea of spatial summation, you can see how there's two different ones coming in. They both are firing at the same time. So it adds together and hits threshold. Now, those are all excitatory. You could also have inhibitory coming in. An inhibitory and excitatory at the same time, they pretty much cancel each other out. Nothing occurs. So summation, temporal, rapid fire, same exact point. Spatial summation, all coming in different points, but the same exact time. So a little about how gradient potentials and summations are working here.